Welcome to this lab. In this lab, we're going to look at create hybrid search with Vertex AI Vector Search. In the task 1, we're going to open the notebook in Vertex AI Workbench and choose a kernel. So let's go to Vertex AI Workbench. Click on the instance name. It will open the Jupyter Lab from here. So this will open a new browser tab. So if you don't see the files like the hybrid search file, so you need to close it and then reset the instance. This one, reset. So it's resetting now. Now I can see the hybrid search file. Open it. So task 2, we are going to install the packages and configure the notebook. Okay, in the task 2, we will install the package and configure the notebook. So you can also take a read in the sentence here. So let me zoom in a bit. So combining semantic and keyword search, a hybrid search tutorial with Vertex AI Vector Search. Vector search support hybrid search, a popular architecture pattern in information retrieval that combines both semantic search and keyword search, also called token-based search. With hybrid search, developer can take advantage of the best of the two approach, effectively providing higher search quality. This tutorial explains the concept of hybrid search, semantic search, and token-based search, and include example of how to set up token-based search and hybrid search. It will take 1 hour for this tutorial, mostly on waiting for the vector search deployment. So why does hybrid search matter? As described in the overview of vector search, semantic search with vector search can find items with semantic similarity by using query. Embedding models such as Vertex AI embedding build a vector space as a map of contents, meaning each text or multimodal embedding is a location in the map that represents the meaning of some content. As a simplified example, when an embedding model takes a text that discusses movies for 10%, music for 2%, and actor for 30%, it could represent this text with an embedding of 0.1, 0.02, 0.3. With vector search, you can quickly find other embedding in its neighborhood. The searching by content meaning is called semantic search. Okay, so you can take a look on this diagram here. So the model put contains with similar meaning closely to each other, embedding in the map. So the model put contains with similar meaning close together in the space. Semantic search with embedding and vector search can make the IT system as much as experience library or short stuff. Embedding can be used for tying different business data with their meanings. For example, query and search result, text and images, user activities, and recommended product. English text and Japanese text or sensor data and analytic condition. With this capability, there's a wide variety of use case for embedding. So why combine semantic search with keyword-based search? Semantic search doesn't cover all the possible requirements for information retrieval applications such as RAG. Semantic search can only find data that the embedding model can make sense of. For example, query or data set with arbitrary product numbers or SKU. Brand new product names that were added recently and corporate proprietary code name don't work with semantic search because they aren't included in the training dataset of the embedding model. This is called out-of-domain data. In such cases, you will need to combine semantic search with keyword-based, also called token-based search, to form a hybrid search. With hybrid search, you can take advantage of both semantic and token-based search to achieve higher search quality. One of the most popular hybrid search systems is Google Search. The service incorporated semantic search in 2015 with RAND-brain model. In addition to its token-based keyword search algorithm, with the introductions of hybrid search, Google Search was able to improve the search quality significantly by addressing the two requirements, search by meaning and search by keyword. So in the past, Building a hybrid search engine was a complex task, just like with Google search. You had to build and operate two different kinds of search engines, semantic search and token-based search, and merge and rank the result from them. With hybrid search support in vector search, you can build your own hybrid search system with a single vector search index, customized to your business requirement. So how token-based search work? How does token-based search in vector search work? After splitting the text into tokens, such as words or subwords, you can use popular sparse embedding algorithms such as TF, IDF, BM25, or split to generate sparse embedding for the text. A simplified explanation of sparse embedding is that they are vectors that represent how many times each word or subwords appear in the text. Typical sparse embeddings don't make semantics of the text into account. Sparse embedding represents how many times each word is used. So the movie feature great music. So there is a score here of 1.0, 1.0, and 0.0. There could be thousands of different words used in text. This embedding usually has tens of thousands of dimensions, with only a few dimensions in them having non-zero value. This is why they are called sparse embedding. The majority of the values are zero. The sparse embedding space work as a map of keywords, similar to an index of books. In this sparse embedding space, you can find similar embedding by looking at the neighborhood of a query embedding. These embeddings are similar in terms of the distribution of the keywords used in the text. The model put contains with the overlap keywords close together in the space. Token build a sparse vector space as a map of keywords. So this is the basic mechanism of the token-based search with sparse embedding. With hybrid search and vector search, you can mix both dense and sparse embeddings into a single vectors index and run query with text embedding, sparse embedding, or both. The result is a combination of semantic search and token-based search result. Hybrid search also provides shorter query latency compared to a token-based search engine with an inverted index design, just like vector search for semantic search. Each query with dense or sparse embeddings finishes within milliseconds, even with millions or billions of items. Section 1, we are going to see create sparse embedding. In this first session, the notebook will generate sparse embedding and build a vector search endpoint. Okay, so we were talking about want to install in the task 2 install packages, configure the notebook. Okay, I select Python 3 as the kernel and run it. So it is running. I'm waiting for the asterisk to come out in order to show it's complete. Not the asterisk, but the numbers. Okay, that is done. The next one, we have to restart the kernel. That is also done. Oh, sorry. Okay, so it's done. Now we go to the next one, that is to set Google Cloud project informations, initialize Vertex AI SDK. Then second, and then the third one, generate a unique ID for this session. That is also done. Now we will need to prepare a sample data set. In this task, you will prepare a data file to build an index for sparse embeddings based on the data format described in the input data format and structure. In JSON, the data file looks like this. Okay, each item should have a sparse embedding property that has values and dimension property. Sparse embedding have thousands of dimensions with a few non-zero value. This data work efficiently because it contains the non-zero value only with their position in the space. As a sample data set, we will use the Google Merge Shop data set which has about 200 rows of Google branded goods. So we use the pandas and import the data into the PD file and then read those PD file into the data frames. So these are where the data come from. It's from the CSV. Now the result is shown in here, as you can see. So in the task for create sparse embedding with the data set, you will create a sparse embedding with TF-IDF vectorizer. Okay, you can also click that to run. With this data set, we will train the vectorizer, a model that generates sparse embedding from a text. This example use this scikit-learn, which is a basic vectorizer that uses TF-IDF algorithm. That is also done. Now it says compress sparse row sparse metric of D type float 64 with 839 stored elements and shape. So the variable corpus had a list of the 200 items such as Google sticker or Chrome Dino pin. Then the code passes them to the vectorizer by calling the fit transform, which is this. With that, the vectorizer get ready to generate sparse embedding. So this is how it looks like, the sparse embedding. So TF-IDF vectorizer try to give higher weight to signature words in the data set compared to trivial words such as the A and of and counts how many times those signature words are used in the specified document. Each value of a sparse embedding represents the frequency of each word based on the count. For more information, you can refer to this section. So in this example, we use the basic word level tokenization and TF-IDF vectorization for simplicity. In the production development, you can choose any other option for tokenization and vectorization for generating sparse embedding based on your requirement. For tokenizer, in many cases, subword tokenizer perform well compared to the word level tokenization and are popular choices. For vectorizer, BM25 is popular as an improved version of TF-IDFs. Split is another popular vectorization algorithm that takes some semantics for the sparse embedding. Get a sparse embedding to make the vectorizer easier to use with vector search. We will define a wrapper function get sparse embedding. So let's run this. Right, that is done. The function passes the parameter text to the vectorizer to generate a sparse embedding, then convert it to the value dimension format mentioned earlier for building a vector search sparse index. You can test the function. So looking for the Chrome Dino pin, so you get the sparse embedding, which is this part. So it returns this value here, and this is value, and then it returns the dimension. Now next we will create an input data file. We will generate a sparse embedding for all the 200 items. Let's run that. Okay, so the result is shown here. So then save them as a JSON-L file and upload to a cloud storage bucket. Let's run that. And run that. So the file is copying now the file. It will take some time, I think. Oh, that is very quick. Operation completed. Section 2, using hybrid search. With these sections of the notebook, you will combine token-based search with semantic search to create hybrid search in the vector search. Task 5, we will create an index endpoint and sparse embedding index in vector search. Let's run this. So this is to build and deploy the sparse embedding index in vector search. To use the index, you need to create an index endpoint. You work as a server instance, accepting query requests for your index. Then the next one, in the task 6, we will create the hybrid index and deploy it to the endpoint. So to build a hybrid index, each item should have both embedding for dense embedding and sparse embedding. Okay, so let's run that. think that is done. I will run this command, and there's a warning, but you can ignore it. And the result is shown here. And you can see this is the result. Okay, the get dense embedding function use Vertex AI embedding API for generating text embedding with 768 dimensions. This generates both dense and sparse embeddings in the following format. That's quite a lot. The rest of the process is the same as the previous example. Upload the JSON-L file to the cloud storage bucket, create a vector search index with the file, and deploy the index to the index endpoint. Let's run that. That's done. So the next one, create index. This should finish less than 1 minute. Dimension 768. Label counts 10. So what it's doing here is using the matching engine index to create a tree index. Next, we will go to Vertex AI Vector Search Index tab and observe the index creation. This will take 4 to 5 minutes. While waiting for the demo, while waiting for the task to finish running, it will take around 30 minutes. We can look at a demo here. So the demo will provide a realistic example that will help you learn how vector search works, explore the semantic and hybrid search, and see re-ranking in action. So for example, this is the website interactive demo. So in this demo, you will experience the power of state-of-the-art vector search technology. Leveraging real-world dataset, the demo provides a realistic example that will help you learn how vector search works. Okay, say for example, let's try the experiment with different options to get a head start with the search. So this is what is given here. And then you just have to put this in the query. You can generate the query, or you can even click the submit. So that is the 24 result return. So because in this query, right, it is asked for coffee maker with the timer. So that is what is showing all the timer here. They have a score as well. The highest score will show first. It's sparse score, re-rank score. Say if I submit just now the vintage 1970 pinball, and that's the result that I will get. So this section describes setting in the UI. You can use it to control the result of the vector search, return how they are ranked. In the task 7, we will run a hybrid query. So after deploying the hybrid index, you can run a hybrid query. So the query for this is the text is kids. So for the query text kit, it generates both dense and sparse embedding for the word and encapsulate them to the hybrid query object. The difference from previous hybrid query is 2 additional parameters and dense embedding and RRF ranking alpha. This time we will print the distance for each of them. So the first part is to run the hybrid query, and the result is printed using these sections of the code. So in each neighbor object, there is a distance property that has the distance between the query and the item with the dense embedding, and a sparse distance property that has the distance with the sparse embedding. These values are inverted distance, so higher values mean a shorter distance. So by running the query with the hybrid query, you get this following result. So in addition to the tokens-based search result that have the kids, keyword, there are also semantic search result included. For example, Google with Google White Classic Youth T is included because the embedding model knows that youth and kids are semantically similar. To merge the token-based and semantic search result, hybrid search uses reciprocal rank fusion, or in short RRF. For more information, you can see later section for what is reciprocal rank fusion. So re-ranking, RRF provides a way to merge the ranking from semantic and token-based search result in many production information retrieval or recommender system. The result will be going through further precision ranking algorithm, so-called re-ranking, with the combinations of the millisecond level fast retrieval with vector search and precision re-ranking on the result. You can build multi-stage systems that provide higher search quality or recommendation performance. Conclusion: in this tutorial, we have learned the concept of hybrid search, how to build vector search index for token-based search with sparse embedding, and how to combine it with the semantic search with dense embedding, as we see on the example. Hybrid search provides a way to mix the best part of the two approach, result in higher search quality in production system. Now, in the task set is optional. It's for the cleaning up. In case you want to delete all the indexes, index endpoints, and class storage, you can use the commands here. Thank you so much. You can end the lab.